Hi everyone, welcome back. So, uh, so we will start talking about our week four topics, okay? And we will start with essentially an introduction to optimization and also something called the least squares and linear least squares, which is related with optimization, okay? The reason we are covering this introductory topic is that uh, the set of controllers that we know as the linear quadratic regulator actually is based on the optimization idea. In fact, it's not optimization, but it's known as optimal control, but it's an extension of optimization. So it's good to have an idea about the general concepts of optimization. And obviously, in the graduate level, we have an optimization as well as an optimal control set of lectures that you can continue digging into this area. Okay, so let's say our topic is Introduction to Optimization and the linear least squares. As many of you pursuing master's or PhD studies will later on cover, this topic, especially the linear part, is also tightly related with the linear algebra courses 501 and 502. That's going to be part of the graduate curriculum. Okay, so what is optimization? Okay, so we can make a somewhat informal definition. Okay, essentially optimization is about finding values of a number of independent parameters or variables that makes a function of those variables, function of those parameters maximum or equivalently minimum. Okay, so let's try to discuss that just a bit. So you have a number of parameters or variables and you have a function of those parameters. Let's say we have parameters alpha 1 to alpha n, and we have a function of those parameters. I will define this in a minute, okay? Alpha 1 to alpha n. So we want this function to be maximum or minimum, and we want to find which variables make that function maximum or minimum, okay? So usually, therefore, alpha is a set of variables that is in Rn, okay? And f is basically a function from Rn to R. So it's a scalar function, a function of multiple variables, but its value is a scalar. So it maps a number of variables to a real number in this case. Okay, let me give you an example, a one-dimensional example. Let's say alpha is just a real number, and f is simply a function from R to R. In this case, we can plot this function, okay? Let's say that this is our function. So this is our independent variable alpha, and this is f of alpha, okay? So this is the f function, okay? So what's happening is that at some point here, this function will achieve its maximum value. Let's call this f max. Okay? And this will happen at a particular value that we will call alpha star. This alpha star is what we are looking for. Okay? This is the so-called optimum point. Okay? And this is a global maximum. Similarly, we might be looking at finding a minimum of that function f, but we will see that basically these are related but somewhat different, but the method to find them is essentially a common method. Okay, so our question that I'm going to reiterate here is basically how can I find alpha star such that f of alpha star is basically larger than f of alpha for all alpha which is in the domain. Okay, so that's the problem. As I said, in general, this is a multivariable problem. There are many variables affecting the function's value, and we want to find all of those values such that the function can have a maximum or a minimum. All right, so now in order to find such a point, we talk about something called the necessary conditions. Okay, necessary conditions means if we are looking at a maximum, the optimum point, these conditions should hold. Okay, so the necessary conditions is that if you look at this point, you see something very important is that if you have a maximum or a minimum, what's happening is that the slope of the function at that point becomes zero. Okay, so you get basically an horizontal line as the tangent to the function. So that constitutes our necessary condition. So if we have f of alpha star larger than f of alpha for all alpha in R, that implies that we necessarily have the derivative of the function with respect to that variable evaluated at that point being equal to zero. That means the slope of the function at that point has to be equal to zero. Okay? So for alpha star to be a maximum, the slope of f at alpha equals alpha star should be zero. Now, what's the problem here? The problem is that, unfortunately, this condition does not guarantee a maximum. If you think about a more complicated function, let me sketch something here. Let's say something like this. Okay, so actually, let me sketch it slightly better. Now you see that there is a minima here. This is called a local minima. Here you see that you have a local a local, again, maxima. Here you have a global, a so-called global minimum. Here you see that there is a so-called a saddle point. Now the problem we have is that the necessary condition holds for all of these points. Okay, so if you look at the necessary condition and try to solve it for alpha, you will find all of those points, okay, in all these points the necessary conditions hold. Necessary conditions hold. That means local maxima, local minima, global maxima, global minima, saddle point. In all of these points, the derivative of the function evaluated at that point is equal to 0. Okay? So we introduce a further set of conditions that we call the sufficient conditions. But as you will see, even these will not be totally sufficient in a way. But at least it's going to be sufficient to discriminate between a minima and a maxima and a saddle point at least. Okay, so let's try to take a look at that. So sufficient conditions. Now when we look at a sufficient condition for a maximum, maximum, and this can also be extended or a minimum. So you have slightly different sufficient conditions for a maximum and a minimum. But let's take a look at what we can further tell about a maximum. Now, if you think about a function which has a maximum here, right? So we know that the slope of the function is 0 here. Slope equals 0. Now, in order to have a maximum, take a look at what's happening before and after that 0. Over here, you see that the slope has to be positive, and over here, slope has to be negative. Okay? So what's happening is that the slope, the derivative, has to be basically going from positive to negative. Okay? Being, obviously it's not a line. Okay? You see that the slope starts, it can be a line, it may be something else, but essentially it's crossing 0 here, but it's positive initially and negative later. Okay? So this is df over d alpha plot. Okay? So if you look at the slope of the derivative, which is the second derivative, right? We see that the second derivative is negative in this case. Okay? So for a maximum, right? Slope of df over d alpha must be negative. Must be negative. So this gives us the conditions, okay, which is based on the second derivative. So I have d square f over d alpha square, which is the derivative of df over d alpha, okay, evaluated at alpha equals alpha star. This has to be negative for a maximum. And it has to be, again, evaluated at alpha equals alpha star. This has to be positive for a minimum. Okay? Now, I have to add here, right, the fact that these are still local. Okay? So note we still cannot guarantee a global maximum or minimum. Unfortunately, it's often the global maximum or minimum that we are looking for. But in practice, these mathematical tools, these conditions, the necessary conditions and the sufficient conditions can only give you a local minimum or a local maximum. Okay? And you would remember from your previous years is that maybe you have already used the slope equals 0 constraints in order to find the maximum or a minimum of a function. Usually, if you have a quadratic function, there is only one maximum or one minimum. Therefore, it's very easy to find that. But if you have a complex function with many local minima and maxima, this becomes a problem. And in fact, this type of maxima finding or a minima finding problem is everywhere. All the learning problems, all the artificial intelligence problems, you are trying to approximate some behavior or approximate some function. Essentially, you are looking for the maximum or minimum of something called an objective function, which is the function that we are talking about. Okay? So another note here, in terms of terminology, note in optimization theory, the function f is called often an objective function. And is denoted by J. Often J is the name given for the objective function. We will see in our discussion about the linear quadratic regulator is that we will define a specific objective function and we will try to maximize that. In fact, we will try to minimize that in order to find an so-called an optimal controller. Okay? All right. So let's generalize this, okay? And let's generalize also the necessary conditions, okay? So let's consider the multivariable case. Which is the generalization, right? Alpha is actually becomes a vector of independent variables up to alpha n. So that is an element of Rn. F, as I said, becomes a function from Rn to R. It needs to be a continuous differentiable function, function of alpha. You can see what kind of problems may arise if this is not continuous or it's not continuously differentiable. In that case, you may have discontinuities in the function. In that case, we cannot really impose our necessary conditions or the sufficient conditions. Okay, so let's have alpha star also defined as a vector. So it's composed of alpha 1 star up to alpha n star, where this is a point in Rn where f of alpha is maximum. Remember, whenever I say maximum, you also have to deduce that it's a similar discussion for a minimum. Okay? So the necessary condition in this case is a vector equation. So if f of alpha star is larger than f of alpha for all alpha in the domain, this implies that you have in fact the derivative of the function with respect to each one of the variables evaluated at that point in Rn. So alpha equals alpha star has to be equal to 0 up to the derivative of f with respect to alpha n, again evaluated at alpha equals alpha star, has to be equal to 0. Mind you that the evaluation has to be done for all values of alpha as a vector. Okay, so you need to substitute alpha 1 for alpha 1 star, or alpha 1 star for alpha 1, and up to alpha n. Okay, so if you put this into a vector notation, so you have a vector which is df over d alpha 1 up to df over d alpha n. Again, this vector evaluated at alpha equals alpha star has to be equal to the 0 vector. Okay, so it's a vector equation in this case. Now this looks similar to the Jacobian matrix. In fact, it's the same kind of operation, but this is a vector. It's always a vector, and it has a special name, and some of you might recall that name. Okay, this particular vector is called the gradient. The gradient of f with respect to alpha, with respect to alpha. Okay, so gradient is a vector. Okay, it just points in a direction, and if you want to interpret it geometrically, it's a vector that is pointing in the direction of the largest increase in the function. Okay, wherever that vector points to, it's where the function is actually having the highest slope. Okay, so in fact, you will see maybe in your graduate years is that there are algorithms which follow the gradient in order to find the maximum point, or algorithms that follow the negative gradient in order to find the minimum point. Okay, why? Because this point, this vector points in the direction of the highest change in the function. Okay, so this also has a special symbol. It's the inverted triangle. So the grad, it's also called the grad sometimes, grad of f, and it's basically this derivative function, derivative vector. Okay. Sorry, alpha n. Now, let's make a distinction here. The necessary condition is that the gradient evaluated at alpha equals alpha star has to be equal to 0. So this is the gradient, not its evaluated form. Okay? So we can basically, we can take this and we can say grad f of alpha evaluated at alpha equals alpha star has to be equal to 0. Okay? All right. Let me put down a note, and then I'm going to show you an example. Sometimes, okay, the function may also have other variables, but you may be interested in a subset of those variables. Okay, in that case, you just assume the variables that are not being of interest as being constants. Okay, so f sometimes can have other variables in it. But you basically define the problem in terms of a number of subset of variables. So you concentrate on them. The gradient is with respect to them. All the rest of the variables are assumed to be constants. Okay, so I will call these alpha variables, the ones that we are interested in. Okay, so but since our focus is on the alpha variables, we assume the rest as constants. Okay. Now let's take a look at an example. Find alpha and beta that minimizes j of alpha and beta. The objective function is 2 alpha square plus beta square plus 2 alpha beta minus 5 alpha. Now, in this case, you see that this is a quadratic function. It only has, it basically goes up to the second order for the terms. So that means if you think about this function, I don't know its exact shape, obviously, but if you think that alpha is one of the variables and beta is the other variable, and this is the j function, it basically is something like this, right? Why? Because this is a positive, the coefficient of the quadratic term is positive. Also over here is a positive. Therefore, this is something like this, okay? So it only has a single global minimum in this case, but obviously if you have negative numbers here, you may be finding actually either a maximum or you may be finding a saddle point, okay? For this case, the necessary conditions guarantee a global minimum we have a quadratic function with positive quadratic coefficients. Okay. Remember that if you have, for example, negative alpha square and negative beta square, in that case, this bowl going upwards will basically going downwards. So instead of a global minimum, you will have a global maximum. But the set of equations that I'm going to solve will be exactly the same. So you need to be careful in that respect. Okay. All right, so what we do is that we talk about the necessary conditions. By the way, if you want to make sure that you have a minimum instead of a maximum, you can also go to the sufficiency conditions and you can solve that as well, or look at the sign in order to make the decision on that. I'm not going to do that, okay? So dj over d alpha, the first variable. Let's take a look at our equation. So this is our j function. dj over d alpha will be 4 alpha plus no term from the beta square because there is no alpha term there, plus 2 beta, okay, minus 5 is equal to 0. Okay, so you see that that gives me one equation in terms of alpha and beta. So I have two unknowns here, so I need at least two equations. In fact, I need exactly two equations in order to uniquely determine alpha and beta. Let's take a look at the second term. So I'm going to also take the derivative with respect to beta, the same objective function. So I will have no term coming from the first term over here. So I have 2 beta from the second term plus 2 alpha, and no term coming from the minus 5 alpha because there is no beta in it, is equal to 0. Okay, so this is my second equation. So I have a set of two equations in terms of two unknowns. You can basically put it into a vector matrix form, and I'm going to do that for a later example. But here I have beta plus alpha equals to 0 from this one. That means I can write alpha in terms of the beta. Okay, so if I put this into so this is my first equation, this is my second equation, put into 1. So I have alpha is equal to minus beta, so I have minus 4 beta plus 2 beta minus 5 is equal to 0. Right, so I have minus 2 beta, put it over there, 2 beta is equal to minus 5, and therefore beta is equal to minus 2.5. Alpha was given in terms of beta, so alpha is equal to simply 2.5. So we know that in this case, we know that this, this point over here is at, in fact, beta at a negative beta. So this is not a very accurate plot, okay? So beta is at, so if I want to sketch this again, this is alpha 2.5 over here, 2.5. Beta is at minus 2.5. So at that point, okay, I basically have my function having its minima. The minima is located at this point in the alpha beta space. Okay? So that completes our example over here. All right. So let me break the video here. I will go with the same sheet, but we will continue in the next video file.